and we'll have Dimitri continue his tutorial on persistent homology computation.
All right. Well, thanks, Aiden. Welcome back. I'm glad to see so many people are back. It's something, I guess. Okay. So we will continue with roughly where we left off. I will very briefly recap just what we were talking about, right? So the main subject that we were discussing was this, well, algebraic topology, but more accurately homology, which I framed as a vector space of non-bounding cycles. And I suggested that maybe the right way, or the easiest way to think of it, was in terms of the dimensions of the various homology groups. So we had the sort of infinite sequence of vector spaces, but the dimension of the zeroth one was really the number of components in the space. The first one was the number of independent loops in the space. Second one was the number of voids. And so these were the examples that I showed, right? So Betty 0 is 3 in this case because there are 3 connected components. For an annulus, Betty 0 is 1. Betty 1 is also 1 because there is one connected component and there is one sort of hole. And for the torus, it was Betty 0 was 1 because there was one connected component. Betty 1 was 2, so there was blue cycle and the red cycle are 2 basis elements for the one-dimensional homology. And Betty 2 is 1 because torus is like a tire tube, right? It's hollow inside, so there's a void inside. Okay, I hope this rings a bell because this is sort of the extent to which I'm going to give intuition for anything. Okay, so we then define simplicial complexes, which, remember, we have some vertex set, just any abstract set that we'll call a vertex set. Any collection of subsets of this vertex set is a simplicial complex if it's closed under containment. So if sigma is in the simplicial complex and tau is a subset of sigma, then tau has to be in the simplicial complex. So the triangulation on the left is a simplicial complex, but on the right it's not because this triangle is missing an edge and this edge is missing a vertex. So that's kind of, and then we had some names, right? So the 0-dimensional simplices were vertices, 1-dimensional simplices were edges, 2-dimensional simplices were triangles, and so on. And we had this, so the chain complex, so the CP was a vector space of formal sums of P simplices. And we had a boundary operator from CP to CP minus 1 that simply took each simplex, as so defining on the basis elements, that took each simplex into this alternating sum of its faces, sort of codimension 1 simplices. So ABC went into BC minus AC plus AB. So it's kind of, it went around the triangle. And so we can think of this boundary operator as this matrix where columns are P simplices, rows are P minus 1 simplices. It's a very sparse matrix. There are P plus 1 entries in a given column, but there are billions of columns. And so the homology, the formal definition that we got to last time was that if we take this boundary operator.
Dimitri, can I ask a really simple question that I've gone through many times in the past, but I can't remember the answer again. But there's some rule to assigning the signs to these elements in the decomposition. And I understand it's arbitrary, but you have to be consistent, if I remember right.
That's right. So well, orientation, once you start digging into it, it's really a partition of the order. So if I have an order of n vertices, I can go from any order to any other order by transpositions. And the things that I get to with an even number of transpositions, that's one orientation. Things that I get to with an odd number of transpositions, that's the second orientation. But the simple rule that makes all of this work is that if you have, so in this case, a triangle, when you drop the ith vertex to get the respective edge, so BC, I drop 0th vertex, right? Yeah, I drop the first vertex. I just take minus 1 to the power I. So this is why it's plus 1, this one plus 1. So that's a rule, but it's a rule that simply makes things consistent. Yeah.
Got it. Thank you.
Yep. Great. So right, so we have this boundary operator, the kernel of it, so all those chains that don't have a boundary is called the cycle group. So it's all the cycles. So here's an example of the blue cycle of a chain that is a cycle in blue, so it doesn't have a boundary. The image of the stuff that comes from one dimension higher are the boundaries. So for example, this red cycle is a boundary because it's a boundary of this triangle, right? So it's well, it's not tautological, but it's a definition. And as I already said in words, a boundary is necessary. So because taking boundary of a boundary is going to give you 0, so that's a key property of this operator. We have that a boundary is necessarily a cycle. So the boundary group is a subset of the cycle group. So you can take a quotient, and the quotient is exactly what the homology group is. So the quotient, if you unpack it, it says that two cycles are equivalent if they differ by boundary. And this is, I guess, exactly what we saw on the torus, right? So I have this picture nearby. So the blue cycle, this blue cycle, and this blue cycle, they're equivalent precisely because they differ by boundary of this green cylinder, right? And so in this picture, I guess, do I have this illustration? I don't. So the blue cycle that went all the way around this way, and this guy, they're equivalent because they differ by a boundary of the triangle. Okay, and so if you wanted to compute the rank or the dimension of this homology group, it's just rank computations, right? So just from this definition, rank of the homology group is going to be the rank of the cycle group minus the rank of the boundary group, which you can then write as a number of simplices minus the rank of this matrix dp minus rank of the other of dp plus 1. Okay, so this, I'm hoping this is a refresher that we kind of are trying to remember the definitions that we discussed last time. Okay, and so last time we also talked about that how to apply this to data, and to apply this to data, we said that, well, what we're going to do is we're not going to compute the homology of a single space, but we're going to compute a sequence of homology groups as we're varying some parameter, and in this picture it was the radius of the balls, right? So we had a bunch of points, we started growing balls around the points, and we started to keep track of the connectivity and the homology groups of these unions of balls. So now the question is, how can we turn this into something that we can, because that's kind of infinite spaces, right? So large, continuous, complicated spaces. How can we turn this into something that we can process on a computer, and specifically into a simplicial complex? And so the way that this is done is as follows. So if we want to use simplicial complexes to represent unions of balls, and one construction that roughly, I mean, the way this works is that we'll have P simplices represent intersections of P plus 1 balls. And so there are several popular constructions. The first one, that's probably the simplest to maybe understand, is what's known as a check complex. And what we say is that if we take this collection of balls, anytime K of them intersect, or not just K, anytime we have an intersection of them, we're going to record this as a simplex. So for this union of balls, what we will say is that these two balls intersect, so we're going to record an edge. So this edge will tell us that these two balls intersect. These three balls intersect, that's going to be represented by this triangle, right? The fact that these three balls intersect is going to be represented by this triangle. If we had higher order intersections, so if we had 4 balls intersecting, we would have a tetrahedron. If we took very large radii, we would have n-wise intersections, and we would have n simplices, n minus 1 simplex to represent this. So there is a theorem that called the Nerf theorem that tells us that the topology, and particularly homology of the check complex, is going to be the same as the homology of the union of balls, and you can kind of see it in this picture, right? So the union of balls has a hole here, and it has a hole here, and the simplicial complex, the check complex, it has this triangle is empty, so that's a hole, and there's a hole around, well, this hole in the union of balls. Is that kind of intuitively making sense? So it's a construction that will capture the topology of the union of balls combinatorially. Maybe. Okay. So another construction that's closely related, but a little bit different, is what's known as the Vietoris-Rips complex. So here we will, it's a clique complex built on the near neighbor graph. So anytime two vertices U and V are within the prescribed distance, or half of the prescribed distance, we're going to put an edge, and then we will count all the cliques in the resulting graph. So in other words, it's going to be all the simplices where every edge, every two-way subset of this simplex is within this given distance. And well, this picture illustrates the difference between the Čech and the Rips complex. So in the Czech complex, we didn't have this simplex, the red simplex. In the Vittorius-Rips complex, we do. So on the one hand, Vittorius-Rips complex doesn't have the same topology as the union of balls, but it turns out that their persistent homology is close, and this is a consequence of stability that I won't get into. But the point is that you can compute persistence for Vittorius-Rips complex, and you can infer something about the topology of this union of balls growing process. So this construction, of course, should be very familiar to you guys because enumerating cliques is a favorite pastime of non-trivial subset of the audience, right?
So sorry, Ken, I just asked about the difference in homology here. So in the Czech complex on this one, you'd have sort of something that looks like a two-hole donut, whereas in the Vittori-Rips complex, you just have a one-hole donut. I mean, I'm using the term donut loosely, but
so in Vittorius-Rips complex, you just have this one cycle. So it's Betty 1 is going to be 1. But in the Czech complex, it's Betty 1 is going to be 2.
Okay.
Exactly right. Yeah. So there are 2 holes versus 1 hole.
I have a question about the Czech complex. So if you were to move the lower left circle, that one, up, so as to close that hole, wouldn't the connectivity of the circle still remain the same? But now we changed the topology.
So if I move this guy up to where this hole closed up, then because now these circles will start intersecting 3-wise, I will have to add this triangle. And so the hole would close up here, and the triangle would close up this hole in the complex.
I see. Okay.
You see, because if I'm pushing this guy up, this point the hole will close up exactly when this point reaches this pairwise intersection. And so there will be a triple-wise intersection.
Oh, I see. So triple intersections are counted differently. I got you. Okay, yeah, I understand.
Right, exactly. If I move it, then the triple intersection will appear different. Okay, one more construction. So this nerve that I mentioned it's a construction that says that if I have a collection of sets, then anytime the sets intersect, I will record this as a simplex, right? So if I have a triple-wise intersection, I will put in a triangle. And this nerve theorem that I mentioned in the previous slide tells us that the topology of the nerve is the same as the topology of the union of these cover sets if they are simple, and particularly it's true if they are convex. And so another construction that is based on this idea is what's known as alpha shape, so Delaunay construction. Namely, the idea is the following. So take your points, take their Voronoi diagram, and now intersect the ball with its Voronoi cell. So now I've clipped all the balls by their respective Voronoi cells. The union, of course, hasn't changed, because if a ball goes into somebody else's Voronoi cell, it's going to be covered by the ball who owns that Voronoi cell. So the union of balls and the union of these clipped balls clipped by the Voronoi cells is the same. These clippings, they're still convex, and so we can take their nerve. If I were to set R to be infinite, it would be the Delaunay triangulation. And if I set it to be some finite radius, then it's been known as alpha shapes. And this is what you see in this picture. And the advantage of alpha shapes over the Čech complex is that alpha shapes are always going to be a subset of the Delaunay triangulation. And so it's going to have the same dimensionality as your input. So if your input is in 3D, you will never have more than tetrahedra. Whereas in the Čech complex, you could have n simplices. And so this is the Delaunay triangulation of these alpha shapes. That's the preferred construction to use in 2D and 3D spaces. And thanks to it, you can handle millions, if not billions, of points in 3D.
Wait, sorry. How do you get a filled-in triangle here again?
So here's an example, right? I have this ball clipped by its Voronoi cell. I have this ball clipped by its Voronoi cell, and I have this ball clipped by its Voronoi cell. The 3 intersections, they intersect in this triple-wise point. So the Voronoi vertex.
Okay.
The Voronoi vertex is exactly equidistant from, well, I haven't defined Voronoi cells, but the Voronoi cells to me are closed, right? So they everything that's less than or equal to in distance, yeah. So that's that's an example of the how we get the triple wise intersection. Yes, makes sense. Maybe I promise I'll get to matrix algorithms in 5 more minutes. Okay, so there's one more construction called lower star filtration, which is what's useful if you want to compute with, like, for example, remember last time we talked about these mountains, and for the mountains, the way you would have this is you would have some triangulation of the planet, and now at every point you would have the elevation value, right, the height, and so I can think of this as a scalar function over the planet, over the sphere, and to compute to turn its sub-level set, so everything below a certain threshold, into a simplicial complex, there is a construction called the lower star filtration. And I was going to go into details about it, but maybe I will actually skip the whole thing because let's get to the matrices. Okay, so the part that we want to do, right, is we're not interested in a single space, but we're interested in this filtration, right? So we have some process that is parameterized by real value. And as we want to keep track of how the homology is changing in this process, and that's what gives us our persistence diagram or barcode, this sort of keeping track of these changes. And so all the complexes that I mentioned so far, the check complex, the Vittorius-Rips complex, the alpha shape, they're all parameterized by this parameter R. And so when a simplex comes in, right, so for example, I form the click in the check complex, sorry, in the Vittorius-Rips complex, that click will stay there for any R greater than whenever it appeared, right? And same with the check complex. As soon as the balls start intersecting, for every larger radius, they will keep intersecting. And so what I really had there is a simplicial filtration. So every simplex has some time when it enters the complex, and then it stays in it forever. So there's this critical radius where the simplex appears, and then it never disappears. So that's actually the setting that we are working in. So it's not a fixed complex, but rather this simplicial filtration. So I stuck in here a slide about lower star filtrations. I'm going to skip this because let's get to the matrices.
Quick question, Dimitri.
Please.
If you go back, sorry, go back to the slides with this. Yeah, so here. So you have H0, which persists for all the way. H1 starting from a middle there, you know, this persists. So the bottom, this one, is that H2 or?
No, this is also H1. You see, here there's a second hole that appears.
Okay.
But it gets filled in here.
All right. So why it? Okay. So it starts from the second hole there. It's still H1, right?
It's all H1. There's no H2 here. Yeah.
Okay, but then the why it didn't go all the way? So you have I mean the horizontal line. I consider that to be timeline. Is it?
Yeah. So you can think of this as time.
Yeah.
So it I mean, this hole died as soon as.
I see.
As soon as this thing was added, right? So it died at this step. So it's died at step Y5. And so I draw this as an interval that is closed at Y4, but open at Y5. As soon as we got to Y5, it's dead. But up between Y4 and up to that point, it's alive.
Okay.
So quick related question. So it looks like you're only going up to like a finitely large value of the radius here. So you're not taking the radius all the way to infinity, right?
Well, so here it's not even radii. There are no radii. It's just a filtration.
Yeah, I know.
But yeah, I stopped it at some point, and this is yeah. You can of course stop your construction wherever you want, right? So you can. This is very useful for Vittorius-Rips complexes, for example, right? So if you cannot go all the way in the complete graph, build all the clicks, you can chop it off at some radius that makes sense from the application. Great. Then let me skip this part. You can take my word for it that there is a construction there. Okay, matrices, the moment we've all been waiting for, right? Okay, so the computation of all of this is actually kind of incredibly simple, and I think we are, as a field, fairly naive in how in what could be done here. So the idea is the following: that we take our complex, although this is not the boundary matrix for this complex, but we take our complex and we take its boundary. So that's our D operator that we saw before. And what's crucial is that we order the columns and the rows by the filtration value. So if this is a triangle representing, this triangle representing this triple intersection, it's the value assigned to it is exactly when these three balls intersect for the first time. So it's when this triangle will enter the filtration. And so this defines an order, and this is the order in which we have to place the columns and the rows. But now once we've ordered our columns and rows this way, and this is boundary matrix in the sense that these guys are parameterized by the simplices, these guys are parameterized by the simplices, and there is a non-zero value if and only if the simplex here is in the boundary of the simplex here, right? Okay, and so the algorithm itself is a kind of very simple greedy reduction that says I'm going to go through the columns from left to right, and anytime I have the lowest non-zero, right, the pivot in a row where I already have a pivot, I'm just going to subtract that column from this column and push the pivot higher. And when I do this by construction, all of my pivots are going to be in unique rows, right? Just because if there was a conflict, I get rid of it. And sort of this, in fact, it's this pivot map, which we call low. So what is the lowest non-zero entry in the particular column is exactly what tells you what the persistence pairing is. So specifically, if I have a persistence, there's some column D whose lowest non-zero is in the row B, then I know that a class was born at B that dies at D. So in other words, this is going to be D, this is going to be B, and I'm going to have a pair BD if and only if the pivot is here. It's basically Gaussian elimination, except we're not, reordering things. We're married to the orders.
But you're just doing one pass, like you just go all the way along once, or is there some?
That's right. I go once, but every column I reduce greedily until so a single column reduction can involve n column addition.
Okay.
Right. So it's not that I do one pass, it's that yeah.
Do you want to eliminate all the columns that are linear combinations of the prior ones?
That will happen automatically through this process, and those will exactly be the positive. They will correspond to the simplices that give birth, that create a class. So remember, so these columns will correspond to the simplices that killed something, that are negative, and the rows of the pivots will correspond to something that is positive. But when something gives birth, it's exactly the situation where the column will reduce all the way to zero. And I will come back to this because I think you're onto a very important observation there. And so maybe one more thing that is useful to remark is that you can think of this, if you keep track of, if you take this extra matrix V that you initialize to be the identity, and you just perform the same row operations in this matrix, you can think of this whole thing as computing this decomposition, R equals dV. And it turns out that this matrix is tremendously important in applications, but I'm not sure how much I will say about it today. But in other words, you can think of this whole thing as computing this funny decomposition. One more remark.
A question here. So for the D matrix, you said each if you look at column wise from each column point of view, there are only two non-zeros because this corresponds to the simplex which has a boundary with this particular simplex, right?
So let's see. This corresponds to the fact that there are two one cycle. Well, in this case, this is a boundary of some. D is a boundary of some graph because there are only zeros per column. And what this corresponds is that the graph has genus 2. So there are two one cycles created in this graph.
Okay, so in some other situation, you may have more than two, right? The boundary.
Right. So if for example, if your total space is simple, so for example, you're computing this for Delaunay triangulation, you will have equal number of zero columns and non-zero columns if you sum across the dimensions. because everything that gives birth will die at some point. Everything that's born has to die, right? That's the moral of the story. Except for one vertex. One vertex will survive. So. Is that okay?
Mhm.
Yeah. Okay. Very sorry. I was waiting with it. Okay. So a couple comments on that. The first comment is that zero-dimensional setting where we're keeping track of connected components is actually special. So you can do that one in n log n time using Kraskell's algorithm. So you can imagine that it's really operation of keeping track of connected components, much like you would use Kraskell's algorithm to compute minimum spanning tree. So that case is genuinely special. But in general, so the algorithm that I described here is cubic time. There's a way to improve it to run in matrix multiplication time, but that's, well, it's not difficult. I won't talk about it today. In practice, what happens is that there are very few columns that are responsible for most of the running time. So there is a kind of fill-in that can happen where certain columns you will have to, in fact, to get, for example, the 0, you have to do lots and lots and lots and lots of operations, and that's usually what dominates your running time. Those are just kind of asides. Okay. Okay. So here's sort of crucial property, or not crucial, but it's an important property of this construction. Namely, it's the following, that you will have this non-zero, or any non-zero, in column I, row J, if this inclusion-exclusion of ranks of lower left minors is non-zero. Yeah, this should be 1. So in other words, so by this notation Rij, I really mean the lower left minor with the at row J, column I, and this is really so Ij minus I rank of I minus 1, J minus 1 minus Ij minus 1. So here, except my numbering I think is screwed up, so that should be flipped, and plus this. And what this what is true is that these lower left minors, they're exactly the same in matrix R. Their ranks are exactly the same in matrix R and matrix D, because all of my operations go from left to right. Right. So they don't change lower left minors. And so what this implies is that even though this decomposition R equals dV is not unique, the pivots, these low R that give us the persistence pairing, they are unique. And maybe one way to rephrase that is that as long as we perform column operations from left to right, we will get the same, and the matrix ends up being reduced, we will get the same pivots. And so this suddenly offers a bunch of flexibility, right? So you can perform your column operations in whatever order makes you happy, as long as in the end you have a reduced matrix, meaning the pivots are in unique rows. Then you're guaranteed that they will be the same, and they will give you exactly the persistence pairing. And that somehow, so a lot of work is built on this idea. So the same story, by the way, is you can also reduce this matrix by doing operations from row operations from bottom up, because again, they don't change. Operations from bottom up won't change the ranks of these lower left minors, and so it immediately follows that you can do operations from left to right, from bottom up, in whatever order you want. But as long as you respect that, you will get the correct persistence pairing. And it turns out these row operations are incredibly useful for computing Vittori-Strips complexes, but that's a different story. Does this make sense? Because that's kind of an important bit. Matrices. You guys like matrices? This should be readily familiar. Okay, well, sorry, no, Gray, you look like you have a question. Great, just ask it. Don't be shy.
Well, no, I'm feeling lost, but I don't know how to answer or ask the right question. Maybe a question is, because I don't understand the working column-wise versus working row-wise, or why that helps. Can you explain it again?
Yeah, why it helps is long, deep story. So the only thing I do want you to easily understand is that you can certainly flip the algorithm that I showed on the previous page to be row operations as long as the operations are from bottom up. So that should follow immediately from this, right? Because so suppose that you believe that this lemma is true, that there is this pivot if and only if these ranks have this obey this inclusion exclusion, and the ranks. So then the question is, when will the ranks not change? If what operations can I do on the matrix D to make sure the ranks of the lower left minors don't change? And if I do column additions from left to right, well, of course that won't change. That's just a change of basis, right? Linear updates. But now if I perform operations from the bottom up, row-wise operations, well, same exact logic, right? I mean, the rank of this matrix will not change as a result of such operation. And so the only thing that I like, why it is beneficial, I won't sort of be able to explain right now, but it should be immediate from this that if it's okay to perform column operations from left to right, it's okay to perform row operations from the bottom up. And the row doesn't matter as long as we get with something where the matrix is reduced. In other words, the pivots are unique.
Does this answer?
Yeah, I mean,
Maybe
I think
yesterday.
so. It's helping. Yeah.
We had one distinction when going over this thing in the past, which is in sparse matrix Gaussian elimination, you have the ability to reorder quite aggressively.
That's right. So here,
and I believe we don't have it here.
Here you have the freedom to perform operations in different order, which could sometimes help, because you could, for example, this non-zero in this column, you could choose to eliminate it using this guy, right? Because
yeah, but like which columns I'm going to eliminate, you can actually reorder that, right?
No. So which columns you will eliminate, you're stuck with, because those will always be the zero ones in the order. But you could reduce, like you can imagine that, for example, I could reduce this column further by getting rid of this guy by adding this column to here, and then maybe during reduction of a later column, I will save myself some effort because I will skip over some operation. So something like that is possible, but that's kind of maybe the extent of what you're allowed to do.
Mm-hmm. Yeah, because in Gaussian elimination, you can just reorder the whole thing and then eliminate in a completely different order.
Well, the main content of that is that in Gaussian elimination, you're allowed to do operations from right to left. Because I mean, your reordering you can interpret as okay, I'm going to do operations from right to left, and that's the one part that you're not allowed to do here. But left right, it still gives you some flexibility, right? I mean, it's not nothing, but it's not as flexible. I can't tell if Edgar is lost in thought or if he is giving up on me.
I'm thinking.
Excellent.
And there's no symmetry, right, in this matrix at all?
There's no symmetry. No, there's no symmetry. No. Okay, let me move on to the next slide. So this information that this computes, right? So this R equals dV or equivalently D equals RU, it's actually useful in various algorithms. So if you see me talk about this topological optimization work, it actually relies on information that you can extract from these matrices V and U. And maybe the easiest is to just show one picture, right? So I have this column matrix R that is reduced. Sigma is the pivot in the column of tau. This turns out represents exactly that, the fact that a one cycle created by this edge sigma is going to be destroyed by this mountain cap, which will be added when we add tau. And in fact, the column R tau stores exactly this blue cycle that is created by sigma, and that's destroyed by tau. And furthermore, the column V of tau stores exactly this red cap, right? So the mountain itself, which is the cap that contains tau in it, and whose boundary is this blue cycle created by sigma. So there's a lot of geometric information contained in these matrices, and well, it's useful. There are applications that rely on it, so it's sometimes useful to compute not just R but also V. Let's see. Okay, maybe one more comment that I forget who alluded to it. Maybe somebody alluded to this. There are various optimizations that are useful. So the fact that d squared equals 0, it implies that if what we already mentioned, that if the pivot in the column of I is in row j, then the column of j is going to be 0, right? So in other words, if simplex I kills simplex j, then simplex j is positive and it created a cycle. That's what this is saying. And so it's actually the naive algorithm that I showed. It will just compute these all of these zeros brute force, right? So it will reduce the column completely until it shows that this column is 0. And one very effective optimization of all of this is what's known as clearing optimization, namely that if we simply reduce these matrices in the order of, in the reverse order of dimension, so first you use dp, then dp minus 1, and so on, then when you reduce dp, you will know which p minus 1 simplices are positive, meaning that they create cycles, and therefore their columns are going to be 0. And so you can just zero them out in the boundary matrix and never have to reduce them in the first place. And this turns out to be incredibly helpful in practice because you waste much less time on these reductions. Yeah, and this is part of why Vitor search complex you can compute with classical cohomology, but again, I won't go into details. Yes. Maybe. There is one more thing that I was going to say, but let me not say it because it will just confuse things more. So let me skip this slide. Okay, so what I was actually going to talk about is various approaches that people have tried to parallelizing these algorithms. And it will be a fairly high-level view, but I think maybe it's useful to discuss in the remaining 20 minutes. But maybe there's also time to pause for questions because people have dropped off and people are being quiet, which makes me nervous.
What are the dimensions of matrix typically? Like, is it more rows or columns or other way? Or square?
So if you combine all of these DPs into one block matrix, right? I mean, you will have the same number of rows and columns just because every simplex will appear as a row and as a column. But it will be the case that, so for example, all the highest dimensional simplices will be, the rows will be 0 because they will have nobody will be mapping into that, right? And so in that sense, but this depends on the problem. So in many interesting problems like Vitor-Search complexes, you will have far more columns than rows, because you will usually build up the Vitor-Search complex up to some dimension, so only k clicks or something. And so k clicks, there will be n choose k of them, but the rows that are non-zero will be n choose k minus 1 clicks, right? And so there's there are just going to be many more. And k is significantly lower than n over 2, of course, right? So
I see. But you're talking about the sparsity of after you factorize already, but the initial matrix is basically square.
No, sorry. So I'm talking about sparsity before I factorize it. So the original matrix is extremely sparse.
I see.
The original matrix will have, so if I'm working with a complex of dimension k, then I'm going to have k plus 1 non-zeros per column. Whereas there can be a billion columns, right? I mean, there can be arbitrarily many columns. The matrix becomes less sparse as a consequence of the reduction, because as you do these operations, you will grow the cycles and the sparsity will decrease.
I was trying to think if you could compute like A transpose A and then do LDL with that. Maybe that also is kind of similar, but I don't know if that has any advantage.
Let's suppose yeah, so that actually is a very interesting topic to discuss because that's closely related to what's called Hodge Laplacian. So it's kind of like a Laplace with a slight change of what you have to be a little bit careful with how you define this, but you get something like a Laplace operator, and then computing that you can sort of compute homology that way. Yeah, but the difficulty is, so for homology computation there are many other tricks that we can exploit because again we just need one rank, right? And maybe if we approximate it we can survive. But this persistent homology, that was sort of what I was trying to convey with this slide, is that we care somehow it's the ranks of every lower left minor that somehow matters, right? Because I really care about these different pivots. And so then it becomes less obvious how to make this work. But maybe there's something there. It's worth thinking about.
Okay, yeah, I thought the rank structure would be preserved in the sense that kind of each column is still a linear combination of others, but yeah, there might be other differences. Okay, thanks.
You mean if you do A transpose A?
Yeah.
Yeah, I mean you're probably right. I need to think through this. Okay, let's discuss this offline because it's I haven't thought about that pretty clearly. Okay, so parallel computation. So there are several kinds of approaches. Some are based on some algebraic insights, some are based on algorithmic slash these non-blocking kind of architecture insights. But all of them actually, the algebraic stuff you can interpret without talking about any of the algebra. So that's what I'll try to do. Okay, so one idea was based on this Myvitor's blow-up complex. And the idea is the following. So suppose that you have a simplicial complex that you can partition into different subsets. So I have a color, right? So I have the green set, the red set, and the blue set. So anything that's in the green set, I'm going to call the green subcomplex. Here it is. Anything that's in the blue set, I'm going to call the blue subcomplex. Anything that's in the red set, I'm going to call the red subcomplex. So that's this guy. And if I split this up into this disjoint union, I need to add some gluing cells. And the gluing cells, they will all have the form that if I have a vertex that falls into a pairwise intersection, I'm going to have to add an edge that connects its two vertices. So this edge corresponds to this vertex, sorry, this edge corresponds to this vertex being in the pairwise intersection. This triangle corresponds to this vertex being in the triple-wise intersection, and somehow glues these the different sets in the disjoint union together, right? The fact that they have this edge translates into this edge, into this pyramid, right? So it's this triangle connected to this triangle. The point of this gluing up procedure is that this blow-up complex, so this construction called the blow-up complex, it will have the same homology as the base complex, right? As this complex K that I'm trying to work with. And so if you perform this construction, then the boundary matrix of this complex has a special structure, right? So the stuff that is only in the green complex is in this corner of the matrix. Stuff that's only in the blue complex is here. Stuff that's only in the red complex is here. And then there is the extra stuff that comes from the blow up, right? That tells us how to glue all of these things together. And so what you can do is you can reduce these bits that are completely independent of each other in parallel. And then you need to somehow combine them and glue them together, basically put all the columns in the correct order, and combine the result by some cascade, by some efficient reduction. So this is exactly what we did, I don't know, 10 years ago with Ryan Lewis. And you can show that this improves somehow time and space complexity a little bit. The trouble with this is that it scales, at first it scales great, but then it plateaus, right? So everything starts being dominated by this combination procedure. So you can of course, if you have a really large domain and you don't have too many processors, everybody has a lot of work, they can do this work, but then eventually you need to bring it all together. And and that time somehow is, I mean, Amdahl's law, right? It will dominate everything. And so that's what you see in the scaling graph, is that it scales for a small number of processors, but then it plateaus. But that's kind of the idea for the domain decomposition. And Aiden, this is, by the way, where Gabe's work is useful, right? Because if you can decompose the point set into these separate regions, then you can then compute them independently and glue them together.
I did not realize that higher level
Yeah.
motivation for that.
Yeah, that's the logic. Does this make sense? Or at a high level, at least. So take a complex, break it up into blocks, compute persistence locally on each block, and then glue it together by putting it all into this inside of this blow up space. Okay, so that's one yeah, okay, Arduino is working on something. That's one idea. Another idea is, okay, it comes from some fancy algebraic construction, but the idea is actually very simple, is if you were to reduce this matrix just by following diagonals, then of course you can, along the diagonal, the blocks don't interact, right? Because I can reduce this block without looking at this block or this block. And so there's a tremendous amount of parallelism in there. So you can actually, if you just reduce this matrix by diagonals, but not just of size 1, but of size some large size, then you can do this in parallel. And this has been implemented. Pieces of software called FAT and DIVA. FAT does shared memory, DIVA does distributed over MPI, and up to details, this is the algorithm that they implement. So they are, so this is some illustration of FAT, but the point is that they are just doing this diagonal reduction where, once this is reduced, all the pivots that are now moved up higher into here, they can now make use of whatever pivots you got from this block. And so you can do this round by round by round. And this somehow corresponds to decomposing your filtration by the value, right? By the radius. Because this is really, simply this is a one radius, this is another radius, and so forth. Does that make sense?
Let me ask a question. So, what you just said, that's because the columns are ordered by the radius, and so that each block column is a range of radius.
That's right. So radius of filtration value. That's right. So columns are ordered by the filtration value. For example, radius for the check complex, and then that's right. So every range of columns is going to correspond to a range of radii. That's right.
But I guess you have no guarantee of the sort of upper triangular structure, or
sorry. So I'm guaranteed that the structure will be upper triangular if I look at all the dimensions together, because faces will always come, like pairwise intersection will happen before triplewise intersection. So that part I'm guaranteed, but I don't have any extra structure here.
then these are not squares.
Well, again, so if I combine all the dimensions, so dp minus 1, dp minus 2, and so forth, all into one matrix, and just order everything by the filtration value, then everything is square because it's all the same simplices appear as rows and columns, and I can break them up into these square blocks, exactly square blocks. But again, I mean, there is sort of there is this connection to some algebraic structure, but the reality is that at the level of matrix reduction, there's no insight here, right? It's just literally that I need to reduce a matrix from left to right. The blocks on the diagonal, they don't interact among themselves, right? So the pivots cannot collide, and so that's all the insight that's really going into this. Yes, maybe. Okay. Then there is a different sort of line of thinking that people have investigated, namely that if you identify, you can sort of take passes and identify these leftmost pivots. So a pivot is leftmost if it's the lowest non-zero in its column and the leftmost non-zero in its row. And if you can identify all such, so suppose you identify a bunch of these pivots, now you can zero out their respective columns, right, to get rid of, and maybe even columns and rows. I forget exactly how these things are done. And then you can peel off those columns, and then you can rinse and repeat them. You can identify the next layer of these, leftmost, rightmost pivots, and reduce the matrix to so that there are no conflicts left, and then rinse and repeat. And so people have thought about using these kinds of algorithms on GPUs. I never managed to get the software to run, so I cannot really speak to it. But it's also a very useful pre-processing step. So the C++ software, it turns out that in some constructions, like the Vittori-Srips complex, there's a whole bunch of these kind of apparent pairs, these leftmost pivots, it's useful to identify them a priori and be done with them. Okay, so what I was going to talk about, but maybe I will just mention very briefly, is an algorithm we had a couple of, well, 4 years ago now, for shared memory. And the idea was the following, right? So I have, so here's the high level reduction algorithm. So we just go from left to right, and for each column we reduce it, and the reduction is check if there is collision, right? Check if our pivot collides with some other pivot to the left, and if it does, then get rid of it. Now, as I mentioned, this can be done in arbitrary order. So this for each column doesn't have to be from left to right. And when we're getting rid of this pivot, we can also, like, I mean, the operations have to always go from left to right, but it's possible to add this column to somebody to the right, even though it's not the final pivot. And so the idea is that you can do this now. You can do this for loop, this reduction, using a bunch of threads at once. But the only thing is you have to be careful. You have to synchronize your operations so that bunch of columns accessing the same bunch of threads accessing the same matrix at once. And so for this, we developed a log-free algorithm where synchronization was done using compare and swap, and with some epoch-based memory reclamation. I was going to dissect this in great detail, but I think I get a sense that folks are out of energy, so I'm going to flip through these slides and assure you that you can solve all the race conditions if you put compare and swaps in the right place. And the point is that it performs well. So it scales pretty well compared to, so FAT is the only other shared memory software. It sometimes can be slower, but scaling still benefits it. Sometimes it can be slower, and so much slower that it doesn't beat FAT, which is a little bit disappointing. But what's useful is you can plug it into, because it's just a reduction, right? There's nothing magical going on. You can plug it into other kinds of software, in particular Ripser, which is the state-of-the-art software for Vittori-Srips complexes. When we plug it into that, it achieves some kind of scaling. I don't know if this is good or bad, but it's better than nothing. Yeah, and so that's the shared memory idea that we had at some point. Okay, I'm going to stop here. This is actually was my conclusion slide. So there's lots of sparse linear algebra, lots of need for parallelization. I think there are lots of opportunities for interaction with other thrusts and collaboration opportunities in general. And in general, so there are lots of people here who are parallel computing folks. I think topology should be like catnip to you, because parallel computation thrives on locality, and topology is all about global information. So you cannot find a more challenging parallel computing problem than topological computation. So I'm hoping this will sort of entice and motivate you to work on this. On that note, I'm going to stop. Thanks.
So that we can spend all our time justifying to reviewers why this is hard. We've done it over years. Fun.
It's easier to solve easy problems. I agree with you.
Dimitri, thank you again. This is actually, we are seeing the end of the slides, at least one version of the end of the slides, in about a perfect time. I'm quite impressed. So in the middle, we lost the most, question asking crowd, which is Sherry and David.
Oh, I see. Is that why the questions died down? Maybe that's what happened then. I see Ariful unmuted himself. Ariful, do you have a question? Or?
I wanted to say thank you.
Oh, I was hoping for a question, but okay.
Something happened to my camera. I don't know.
Oh, okay. Thanks.
I learned a lot, but this is still significantly difficult for me. But I was actually using Wikipedia to learn some of the term while you're talking.
Oh, that's a major failure on my part, and you should have just asked. I would have gladly explained.
No, it's a good. I learned something at least.
Great. Maybe it will motivate you to work on this now.
Sure. Yes, we always look for hard problems for prioritization.
Well, there you go.
So Dimitri, how big are the problems that people are trying to solve practically in this space?
Well, sort of we're always constrained by what the software can handle. So I mean, like in application cosmology, it would be interesting to run this on trillions of simplicity, right? So certainly yeah, tens of billions is certainly like common, right? With I mean, that one problem that is very serious that I kind of glossed over is that these constructions like Vittori strips, they create this combinatorial explosion, right? So if I'm interested in all the k clicks, right, then if my k is the problem becomes the construction is exponential in k, right? So if I'm you know, if I have 100 points and all I'm interested in is, you know, edges, 2 clicks, 10,000 is my upper bound, right? The second I go to triangles, 3 clicks, I am suddenly in you know, 1 million. But then if I want a tetrahedron, that's already, you know, 100 million, right? And it just keeps going from there. And there are, in many applications, you can get away with you know, dimension 3 maybe, so in low dimensions. But there are applications in neuroscience where people are interested in these middle dimensions, and we're completely like, it's hopeless. We don't know what to do. There are some tricks. I shouldn't say that it's hopeless, but there are some tricks, but they don't get us to where we want to be. Yeah, and so that problem is that people often think of persistence as being only applicable to small problems because they think of Vittori strips construction and they think of k being 3 or 4 or something. And because if your k is 3 or 4, you're suddenly, you know, 1,000 points is already a lot.
Okay. All right, thanks.
Thank you, Dimitri. Again, I'm going to stop recording.